Okay, so basically everything that we've done up till this point is stuff that I would say most people that do pure model theory uh, have encountered at some point. I mean, I think like if you are part of the community and are like someone that has finished their PhD and call themselves a model theorist, then probably like everything that I've said about NTP2 at least and simple theories is something that you've heard of and have some awareness of. But actually, what we're going to do now is a theorem that somehow no one knows. So I think like I made like special effort to work and find a sort of clean way of presenting it. So hopefully it's interesting. But it concerns a class of theories called NTP1 theories, which as a class of theories is certainly well known. But this result, which tells you somehow a characterization in terms of something that looks like dividing, I think is very interesting, and there's still a lot there that needs to be understood. So this will probably take 2 days, maybe 3 days, and then we'll be done. So this is sort of the last thing we do. So I will get screen sharing going. And I'll warn you that in about 20 minutes, there will be an alarm that goes off, and then I will have to quickly run to the other room very quickly and then run right back. But I'm doing a favor for someone. Okay, so now we're moving on to NTP1, which is the same thing as NSOP2 theories. So let me recall the definition, although we've talked about this before because this came up when we talked about the tree property. So the definition is as follows. So the formula phi xy has SOP2 if there is a collection of tuples a eta in 2 to the less than omega, such that, okay, the first thing that happens is paths are consistent. So that says for every eta in 2 to the omega, so that's a path through the full binary tree. If you look at tuples indexed by nodes along that path, you get a consistent partial type. And the second thing is it says that incomparables are inconsistent. So whenever you take eta, which is incomparable with nu, in 2 to the less than omega, then phi x a eta phi x a nu is inconsistent. Okay, then T is NSOP2 if no formula has SOP2 modulo T. Okay, so this looks familiar. We had exactly this tree property before when we talked about the tree property of the first kind, except there's one small change, which is here, the index set in question is not omega to the less than omega, it is 2 to the less than omega. So you're looking at a binary tree. So TP1 is the same with 2 to the less than omega replaced by omega to less than omega. So now your tuples are not just indexed by a binary tree, but rather an omega branching tree. So an observation which is useful. So SOP2 equals TP1 at the level of formulas. So if a formula has SOP2, it has TP1. And so the other direction is also true, but trivial. So of course, if you have an omega to the less than omega indexed collection of tuples such that paths are consistent and incomparables are inconsistent, then you can just restrict that to the subset, which consists of those sequences who only take on the values 0 and 1. That's the full binary tree sitting inside this countable branching thing. And of course, paths are still consistent and incomparables are still inconsistent, because incomparability in 2 to the less than omega is the same as incomparability in omega to the less than omega, and paths in 2 to the omega are the same as paths in omega to the omega restricted to that set. So so it's easy to see one direction, and the other direction is kind of an exercise, but I can sort of draw a picture. So by compactness, it suffices to prove that if you have SOP2, you have like, let's say, an in-branching tree of height omega for every n, right? Because if you can build arbitrary width, then of course by compactness you could build one of countably branching width, and then you're done. So how do you get one of width 3? Well, you could look at this thing sitting inside of your omega branching tree, or sorry, inside of your binary tree, and then above each one of these you could look at the same shape. So now I'm going to treat this as like my root node, and these things here will be like my next level, and these things here will be like the next level. These things here will be the next level. And these things here will be the next level. Does that make sense? No, that's not right. So what I meant to say is these things here will be the next level. So anyway, I mean, you can, what did we find? Inside the binary tree, we found something that looks like a 3-branching tree by copying in this way. And so this you should consider as an exercise. But it's not so hard. You just have to find for every n an in-branching tree living inside of 2 to the less than omega such that paths are consistent. So what you want is that inside this tree that you find, a path through that tree is a subset of a path in 2 to the less than omega. And you want that incomparables in this tree that you find are incomparable in 2 to the less than omega. And this picture that I just drew is some approximation how you might do that for the case of 3. And then you can just try to write down what that looks like in general. So if a formula has TP1, then it has SOP2 and vice versa. So then you might wonder, okay, why is there this name change? And the reason that these properties SOP1 and SOP2 were introduced is because there's a whole hierarchy of properties called the SOPN hierarchy, and these sit at the right place in the hierarchy. So that's what I'm going to define next, which is the SOPN hierarchy. Okay, so suppose n is greater than or equal to 3, then we say T has SOP n if there's a formula phi x y and indiscernible sequence ai I less than omega, such that, okay, two things happen. So one of them is that phi witnesses the order property with respect to this collection of tuples in the following way. So we have that oh wait, sorry, I'm calling it phi, not psi. So phi ai aj holds if and only if I is less than j. So you have this collection of tuples which is somehow ordered by this by this formula. And we want to understand to what extent it looks like a linear order. And what we're going to say is that it approximates a linear order in the following way, namely it doesn't admit loops of size n. So if I look at phi xi plus 1 as I ranges over 0 all the way up to n minus 1. Sorry, n minus 2, because we have a plus 1. So you go all the way up to n minus 2. And then you take the union of that with phi x n minus 1, comma x0. This is inconsistent. So what this is saying is that you can't find, so if we're thinking about, like, I don't know, the case of SOP3, you can't find 3 elements like x0, x1, and x2, such that you go this way by phi, you go this way by phi, and you go this way by phi. So you're emitting a loop like this. Now, why is that an interesting property? Well, you might think about what happens in an actual linear order. Like if you take an actual linear order, what happens if x0 is less than x1, x1 is less than x2, and x2 is less than x0? Well, those things all have to be the same, or you get a contradiction because it violates transitivity. So before we saw that if you're thinking about a strict linear order, before we saw that, like, if you're not stable, you have the order property, and that means that you can have one of 2 additional properties. You have to have the independence property, or you have to have the strict order property, which tells you that there's an interpretable partial order living inside of your structure. So in the case that you have a strict partial order around, then of course you have SOPN for every n, because transitivity tells you that you have these loops being inconsistent. That's just an easy consequence of transitivity. So what you can think of these properties as doing is saying that even if you don't have say, a interpretable partial order, perhaps some of these downstream consequences of transitivity are still preserved. And in this way, as n gets higher and higher, you're thinking about your relation as getting closer and closer and closer to being a transitive relation. Of course, that's not really right, because you can be SOPN for every n without being a partial order, yet you're still getting closer and closer as you get up. So these are like approximations to strict order. And SOPN stands for stronger order property n. So, the nth stronger order property. So one thing that you can check is that for all n, if you are in SOP1, that implies that you are in SOP2, and that implies that you are in SOPN, which implies that you are in SOPN plus 1 for all n greater than or equal to 3. And this is a nice exercise. To check these implications. So the implication that NSOP1 implies NSOP2 is one that we discussed. So this follows just from the tree definition of these 2 properties. The fact that SOP3 implies SOP2 is something that you have to work on. That requires some thought because you have to sort of relate having something that looks like a linear order around to finding a tree. And it's a nice exercise. You can think about intervals in linear order and try to build a tree from intervals in linear order that SOP3 gives you. And then for the rest, it's also not so difficult to just check that if you have SOP 4, then you have SOP3, possibly with a different formula. Okay, so that's nice. And I will mention that these arrows do not reverse for n greater than or equal to 3. So if you have SOP3, that does not imply that you have SOP4. And there are examples at each stage of the hierarchy saying that these are different. So SOP3 is different than SOP4, which is different than SOP5, and so on and so forth, even though you have a containment going one way. Now, the other questions, so NSOP1 equals NSOP2 equals NSOP3, and these things. Okay, so these were all open questions, which came out in the early 90s and which are very difficult. So this one was probably resolved in the course of this class being taught. So there's a recent preprint due to Masoud Permadian and Ali Balizadeh, who via Rashkovsky construction constructed a theory which is SOP2 but NSOP3. So of course that hasn't been refereed yet, so it's probably too soon to say that it's definitively settled, but there's a reading group now working through it, and it seems very promising. So that's an exciting development, something new. On this other direction here, we still have no idea. So whether or not SOP1 and SOP2 are the same is an interesting and difficult open problem that I would love for someone to solve. So that is one problem. Another question which is worth mentioning is we spent all this time talking about NTP2 theories, and the examples that witness that SOPN is different than NSOP, that is different than SOPN plus 1 are all theories that have TP2. So there's a question that's due to Artem Chernikov, which is the SOPN hierarchy strict in NTP2 theories? Namely, if I restrict attention just to the NTP2 theories, is there something that collapses here? And I mentioned this problem a few weeks ago. So I think this is another nice question. So cool. So that's all I wanted to say. So we're going to start talking about higher formulas now, which are a way of talking about formulas that don't divide, except maybe they divide, but you want to sort of specify a sequence with respect to which they don't divide. And if that sequence is very generic, then you can think of that as in some way a big set. So why these are called higher formulas, I'm not 100% sure, but that's the name that we were given. So we're going to go with it. So higher formulas. So here's a definition. A higher formula so I should say all of the stuff that I'm going to be talking about now is in a paper of Marian Thimeliaris and Saharan Shella called Model-theoretic Applications of Cofinality Spectrum Problems. And then, but it turns out that this part of the paper has nothing to do with cofinality spectrum problems. It's just about NTP1, which I think is perhaps why these results are not so well known. I think the technology of cofinality spectrum problems is very intimidating and technical. And I think this paper is also particularly technical and intimidating, using cofinality spectrum problems to solve problems about, say, bounded arithmetic and whatnot, which are a little bit far from core model theoretic questions, although it's still very interesting. And I think that this was sort of hidden in one of the final sections of that paper. But I think the ideas there are very interesting and, like I said, worth being thought about. So let's define a higher formula to be a pair, or let me say a higher formula over A. Is a pair phi xy p of y. So notice that the parameters of the formula match the variables of the type. So it's a pair like this where phi x y is a formula that can possibly use parameters from A, and P of y is a global type, finitely satisfiable, in A, such that if AI, I less than omega, is a Morley sequence, over A in P, then phi x AI I less than omega is consistent. Okay, so what does this look like? The idea is I've got my monster model, I've got some subset A, and I'm looking at my formula, and I start realizing a Morley sequence inside of P. And if I move my formula along that particular Morley sequence, I get something consistent. So the idea is the formula and the type are the higher formula together. And the idea is that the type, the idea is like it's like a higher formula because the parameters are not really fixed. They're like somehow ethereal. Like I haven't fixed a point, which is the parameter. I fixed the type of the parameter, which is just described to me by P. So somehow it's like it's like, you know, it has shed its earthly existence, and now it has just this kind of shadowy existence in the form of a type. So you don't actually know what the parameter is. You only know its identity up to automorphisms described by this partial type. And the reason that's going to be important is because soon we will want to talk about how higher formulas interact, and neither of them have fixed parameters. So the parameters will somehow be like generic instances of realizations of the different types. And that extra degree of freedom is valuable. But one thing to think about is what happens if you're in a simple theory and you're looking at a higher formula, or even in an SOP1 theory and you're looking at a higher formula. Well, this sequence is a Morley sequence, and your formula doesn't divide with respect to it. Now, if you are in an SOP1 theory, then that tells you that it doesn't Kim divide because of Kim's lemma, right? Like, what do you have to show that something doesn't Kim divide in an SOP1 theory? You just have to exhibit a single Morley sequence with respect to which it doesn't Kim divide. So if you take a realization of the type over A, call it little a, then if the formula is higher, you know that phi xa does not Kim divide. Or if you're in a simple theory, then you know by Kim's lemma, the real Kim's lemma, that phi xa doesn't divide. So now we're in a context where that's maybe not true anymore, but what we can do is we can still sort of look at the behavior just with respect to certain sequences and restrict our attention just to those. Maybe there are some other sequences with respect to which it will divide, but we don't care. We're just going to restrict attention to the ones with respect to which it doesn't. Okay, so that is what a higher formula is. And let's just make a definition for like how these things might interact. So definition. So suppose phi p and CQ are higher formulas over A. We say phi p is contradictory to CQ if for some equivalently all Morley sequences in P over A. So this is going to be, so this is like tensor omega. So recall that's my notation for the type of a Morley sequence over A. And B bar, which realizes Q, which is a Morley sequence in Q, not just over A, but over A and the Morley sequence that I took in P. Then if I look at all of the instances of the AIs and all of the instances of the BIs in their respective formulas, this is inconsistent. Okay, so let's see what this looks like, because I think this is confusing if you see it the first time. So here we are inside of our monster model, and we've got some set A, and I first start, oh, there's my alarm, I'll be right back. Okay, sorry about that. So, right, so I'm sitting inside of my model, and I start realizing P. So I realize P, and then I realize P over A and the realization, and I realize P over A and the first two realizations, and so on and so forth. So step by step, I'm generating a Morley sequence in P. And then over all of that stuff that I've built so far, oh goodness. Okay, then over all the stuff that I have built so far, I start realizing a Morley sequence in Q. So I realize P, I realize P, I realize P, I realize P, I do that omega many times. And then I start realizing a Morley sequence instead of Q. I realize Q, I realize Q, I realize Q. I do that omega many times. And at the end of all of that, I have two Morley sequences, which are somehow independent of each other. Because, you know, inside of Q, I was realizing it not just over A, but over A and the first Morley sequence. So what that looks like is I start realizing this sequence, which is going to be in P. And then over that, I'm going to start realizing Q. So this is Q tensor omega. And I've written, I mean, I've sort of marked these in green because what it meant to be higher was if I take my collection of, tuples and I start plugging those into phi, those have to be consistent. And if I look at my second collection of tuples and I plug those into psi, those are also consistent. But I'm told that collectively they're inconsistent, which means that if I take the union of all of this stuff, that is inconsistent. So that's what it means to be contradictory. Notice that there's no reason a priori for this notion to be symmetric. So we defined what it meant for phi to be contradictory to psi. And I first realized P, and then I realized Q over the realizations of P. So, you know, is it the case that if phi is contradictory to psi, that psi is contradictory to phi? Should that be symmetric? Well, it turns out that in general it's not, but there's a sort of nice characterization of when it is, and that corresponds exactly to NSOP3. So that's going to be what we're going to show today. And then next time, and probably a little bit after next time, we will characterize in TP1 theories in terms of bounds on the number of higher formulas that you can have which are contradictory to one another. Okay, so let me make some further observations before we get into the proof. First off, it's sometimes useful to additionally define phi p is k contradictory. Sorry, that's illegible. Let me fix that. So phi p is k contradictory to Cp if for some, again, equivalently all, a bar, which realizes p to the k. So this is a Morley sequence of length k. So I just realize p k times, and then I'm going to realize q k times. Then these k instances of phi together with these k instances of psi are inconsistent. Okay, so this is just like a finitization of the idea of contradictory. And what is nice about that is that you know from compactness that if two things are contradictory, then they have to be k contradictory for some k. Okay, so now we've just specified the k. Great. Another thing that I want to observe, so let's call this a lemma. Is suppose phi p and Cp, or sorry, let's call it Q, are higher formulas over A. And what we will do is we will define capital phi x y0 yk minus 1 to just be the conjunction of I less than k phi x y I. So I've just taken the conjunction of x, k instances of little phi, and I'll do the same for capital Psi. So capital Psi x y0 through yk minus 1 is just the conjunction of I less than k Psi x yi, like so. Okay, then two things happen. So one of them is that the pair phi p tensor k is a higher formula over A. And two, if phi p and CQ are k contradictory. Well, I should say this with order. So we're not yet working in a context in which these notions are symmetric. So if phi p is k contradictory to CQ, then capital phi p tensor k is 1 contradictory to capital Psi Q tensor K. Okay, why? So I won't even really write down the proof because I think it's clear and easy just to think about. So what did it mean to be a higher formula? What it meant to be a higher formula was I give you a formula and a type, and if you realize a Morley sequence inside that type, then the formula is consistent along that sequence. That's all it meant. Now, what does it mean to realize a Morley sequence inside of P? Well, I realize P, and then I realize P again over the realization, and I realize P again over those two realizations, and so on and so forth. Now, P tensor K is just the type of a Morley sequence of length K inside of P. So if I take a Morley sequence inside of that, then what am I doing? Well, I'm looking at first the type that says I realize P, and then I realize P over the realization, and I realize P over the realization. I do that K times. And then over that, I do it again. But if I realize those the second K elements over the first K elements, if I unravel what that type is saying, that's the same thing as saying I realize P, and then I realize P over the realization, and I realize P over the realization, and I do the whole thing 2K times. And then if I realize P tensor K a third time, then I get a sequence of length 3K where each element realizes P over all the elements that are before. So a Morley sequence inside of PK is the same thing as a Morley sequence inside of P that I've just broken up into K-length blocks. So of course, if the union of phis along that is consistent, then the union of capital phis along this collection of K blocks is going to be consistent because those are literally the same. They're expressing literally the same thing. I mean, they just say the same instances of phi. Does that make sense? So higher is easy. And then it's the same thing to say that you get from K to 1. What is one instance of capital phi? That's the same thing as K instances of phi. So it's a very easy translation, just using the definitions, to say that, okay, if you have two types and you know that they're K contradictory in one direction, then by replacing those formulas with conjunctions and replacing the types with tensor products, you can bring that number from K down to 1. And this is going to be something which is convenient for us to do. Great. And let me maybe say the converse, which is about being not contradictory. So if phi p is not, let's say, incontradictory, to CQ, then capital phi, P tensor K, is not, okay, floor of n choose K, or sorry, n divided by K, contradictory to psi, capital Psi, Q tensor K. And this again is the same thing. I mean, so if capital phi P tensor K is floor of n divided by K contradictory to psi Q tensor K, then what does that mean exactly? That means that if you unraveled the definition, you find, greater than n many instances of, under n many instances of phi, and under n many instances of Q, psi Q, which are contradictory to one another, and that meant that phi and Q had to be incontradictory to one another. So this again is just unraveling the definition. This is a kind of direct translation. Okay, so now we're going to come to the theorem of the day. It's really a lemma, so let's call it that. Lemma. So the following are equivalent. Oh, actually, we have to do a lemma before we get to the lemma. So we're almost definitely going to need to spill over into Friday now that I think about it. But okay, it's fine. It's the last theorem we're going to do. So if we have to talk about it on Friday, then that's perfect. So the following are equivalent. This is going to give us a new characterization of SOP3, which will be useful to relate SOP3 to higher formulas. So the first thing we want to say is T is SOP3. 2, we'll say there are two formulas. So let's call them C0, XY, and C1, XY, and an indiscernible sequence. AI, I less than omega, such that A for all k less than omega. If I look at C0 x AI for I less than k, and C1 x AI for I greater than or equal to k, this is consistent. But B says that if I is less than j, then if I look at C0 x aj, well, let me write it this way. And C1 x ai, this is inconsistent. So what does this property say? I mean, I imagine that I have some indiscernible sequence, right? And if I choose some k and I relate to all of these things down here via phi0, sorry, psi0, and I relate to all of these things via C1, that's consistent. That's totally fine. So you can imagine phi0 as saying x is bigger than y. And you can imagine C1 as saying x is less than y. And then what am I describing here? I'm saying, I'm like describing a cut. I'm saying I'm greater than all of the stuff that I've touched with green, and I'm less than all the stuff that I've touched with blue. And if I'm imagining my sequence as being like the natural numbers, or let's say the rational numbers that you can realize cuts, then all I'm describing is like a cut in my linear order. And so, you know, if I'm really in a linear order, which is how I'm sort of thinking about this, then that's totally consistent. However, if I look at condition B, what that says is if I switch, so I don't know, let's choose an I here and a J here, and I relate to this one via C1, and I relate to this one via C0, this is inconsistent. Now, why? Well, again, think of the interpretation of C0 as saying x is bigger than y. So I can't simultaneously say I'm bigger than j and I'm less than I. That's inconsistent. So, you know, if you have this interpretation, then this makes sense. This sort of corresponds to the way that you see cuts in linear orders. Okay, so that's number 2. This is this other condition about these two formulas. And the third point is just sort of this like uniform version, which says there are in m less than omega and formulas C0 xy, C1 xy, such that A is as above. So if I split, I can say C0 to everything below and C1 to everything above. And then B is going to just say that for all I0 less than dot 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 less than I m minus 1, J0 less than dot 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 less than J n minus 1. If I say C1 to the i's, say L less than m, oh wait, less than J0 less than J0 n minus 1, yeah, okay, this is how I want it. C0 x a j L prime less than n. This is inconsistent. So it's the same thing, it's just that I've gotten rid of this fact that, if I take a single instance of psi below a single instance of, if I take a single instance of psi1 less than a single instance of psi0, I get something inconsistent. Now maybe I need to fatten it up and use some more. So this is useful just because this is often what compactness will give you in arguments, and then you need to reduce it down to 1 to get the definition. So let's start in on proving this, and then I think we will finish it next time. So first, to if and only if 3, because you can replace C0. Well, okay, so let's do this first. So 2 implies 3 is clear because you can take n equals m equals 1. So, 3 talked about having n instances of C1 and m instances of C2, and 2 just talked about having a single instance of C1 and a single instance of C0. And okay, so then that, if you just take n equals m, then you get exactly 2 back. Now the other direction is easy just by replace C0 by a conjunction of m instances and replace C1 by a conjunction of n instances. So those things are easily seen to be equivalent. If you just replace the formulas by conjunctions, then you reduce n and m down to 1. Because if you have the conjunction of n instances being inconsistent with the conjunction of m instances, then that's the same thing as saying those conjunctions are 1 inconsistent with each other. So that's good enough. So the harder thing will be, or actually, I suppose, okay, let me say something better, which is we should take maybe a conjunction of capital N instances where capital N is the max of n and m, and replace our sequence ai, I less than omega, by a prime I less than omega, where a prime I is equal to, okay, a n times I, a n times I plus 1, dot, 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 all the way up to a n times I plus n minus 1. So now I have an indiscernible sequence consisting of blocks of length n, capital N. And of course, if the original sequence was indiscernible, then this one is indiscernible. And now if I take my conjunction of formulas, if those are inconsistent, then I get the one inconsistency that I was looking for. Okay, so that's going to be it for today. And then that only did the equivalence of 2 and 3. So we need to actually relate these to SOP3 in some way. So once we do that, then we can relate these to higher formulas, then we can start proving the theorem. So next time we will get pretty deep into the thick of it. But then I think we'll probably finish on Friday, which will be the last day. Okay, so are there any questions that people wanted to ask?
Nick,
Yeah.
just a question about the definition of contradictory. Does it make sense to maybe generalize it to more than 2 formulas? Like if you realize the second over the first and the third over the second and the first.
Sure. Yeah, you could totally do that. So you could say that like 3 formulas form like a contradictory sequence or something, where you say like, because of course the order matters. So
Yes,
you
yes.
sort of have to say like a contradictory sequence or something. But you're saying like if you had three formulas, you could say first realize the first, then realize the second, then realize the third generically. And if you do that, then they're inconsistent. And that makes perfect sense. Interesting something.
Is it interesting?
Well, is it interesting? I'm not sure. I don't see a use for it, but that doesn't mean, I mean, so basically like we are now in, you know, in the Wild West or something. I mean, like we're in a part of model theory that people have not really, you know, like it's not clear what the theory for in TP1 will be, if there is a theory. You know, like the whole point of this discussion of Kim independence was to give a structure theory for NSOP1. But before that existed, it was like not clear what the structure theory for that was going to be. I think that's sort of the state we're in for NTP1. So any definition you have, you can play with it, and maybe something interesting will pop out. I mean, at the moment, we really don't know what's interesting and what's not because we don't know what the theory looks like. So yeah, play with it. See if something pops out. Maybe something will.
So we just going to show that you have for NTP for NSOP3 you have symmetry for this notion.
Exactly. Yeah.
Maybe you can get something for NSOP M for higher M.
Yeah, maybe. Yeah, that's a good point. Unfortunately, this theorem that I'm just now stating in terms of these two formulas, I don't know a suitable generalization of that to NSOP4, you know, for SOP4. So that in itself is already kind of an interesting question. If you can come up with a condition for SOP4 that sort of looks like this one. And so I'll make sure to sort of flag what's special about SOP3 when we do this proof next time, and I'll mention why it seems hard to generalize. But that doesn't mean that the generalization is false. It just means that we haven't imagined the correct generalization yet.
Okay, thanks.
Okay, so have a wonderful Monday, and I will see you all Wednesday.